Welcome to Sleepcast, probably the most boring podcast in the world. Sleepcast is created to help you relax, slow down, and gently drift off to sleep. There's nothing you need to remember and nowhere else you need to be. Simply get comfortable, close your eyes, and allow tonight's quiet story to carry you away. And now, we hand things over to our two hosts for today's episode. Rest well and enjoy.
So I want you to just look down at your shoe for a second.
Always a good place to start.
Right. Because before that shoe got to your foot, it most likely survived, 40-foot rogue waves in the North Atlantic.
Oh, easily.
It navigated these incredibly tense geopolitical maritime choke points, probably bypassed pirate-infested waters.
Yeah.
And it did all of this while locked inside a rusting corrugated steel box.
Stacked like, 10 stories high?
Exactly. 10 stories high on this floating piece of infrastructure that's literally the size of the Empire State Building. Yeah. So today, we are taking a deep dive into the hidden, hyper-regulated conveyor belt of global trade. We're going to decode the invisible architecture of how the world actually moves its physical inventory.
It's honestly a remarkable paradox. We are entirely surrounded by the end results of globalized trade. I mean, everything in the room you're sitting in right now.
Yeah, almost everything.
But the actual mechanisms, the immense ships, the Byzantine treaties, the structural physics, they just remain completely out of sight for the average consumer. So today, we're exploring how humanity transitioned from a really chaotic era of dangerous, highly unpredictable wooden ships to this synchronized, heavily standardized global network.
And to map that out, we are working through a really fascinating stack of source material today. We have the official history and founding documents of the International Maritime Organization, or the IMO.
Right, the global rulebook.
Exactly. Plus, we're looking at the intensely personal, multi-generational corporate archives of the shipping titan A.P. Møller-Maersk.
Which is just a wild story in itself.
It really is. And then, to anchor all of this history in, physical engineering reality, we are examining the highly specific regulatory text of the 1972 Convention for Safe Containers.
Which gives us a very comprehensive vantage point, because by weaving these sources together, we can really trace a distinct narrative arc. We're looking at the evolution of shipping from a highly fragmented, localized, and frankly, incredibly risky endeavor into a globally synchronized system.
A system that requires, unprecedented geopolitical cooperation, right?
Yeah, exactly. I mean, the open ocean is essentially the ultimate Wild West. Bringing any semblance of order it took a century of trial, error, and just staggering human ambition.
Yeah, and before we can analyze those global maritime rules that basically run the modern economy, we kind of need to understand the raw human risk that defined early shipping. The Maersk corporate history sources take us back to the late 19th century, to a man named Peter Maersk Møller.
Right. And it's important to note he wasn't some boardroom executive.
No, not at all.
He was a sea captain operating in an era where the ocean was fundamentally unforgiving. He came from a long line of seafarers. And in the late 19th century, he was commanding a bark, a traditional sailing vessel named the Valkyrian.
And in 1883, his entire life trajectory just violently alters, doesn't it?
It really does. The Valkyrian, which was actually owned by his father-in-law, was on a transatlantic journey from Newport in the U.S. over to Glasgow, Scotland. And in December of that year, it encounters severe weather and wrecks completely off the Scottish coast.
Losing his ship in the 1880s, that wasn't just a financial setback. That was often total ruin.
Total ruin. And the personal tragedy actually compounds the professional one for him here.
Yeah, he makes it back home to Denmark, only to learn that his father-in-law has passed away. So the family shipping business is just immediately dissolved.
Gone overnight.
So at 50 years old, Peter finds himself with no ship, no income, a dissolved family business, and a family to feed. It's a massive crisis.
It is. And most individuals in that historical context, facing complete destitution at 50, they would have sought a safe, quiet job on land.
Or maybe tried to find work as a subordinate officer on someone else's ship.
Exactly. But the sources highlight a profound defining pivot here. Peter decides to completely re-educate himself.
Which is wild.
Yeah, he enrolls at the Bogo Navigation School to study engineering, specifically focusing on steamship technology. He recognizes that the era of wind-powered maritime trade is ending, and the future belongs to coal and steam.
It's basically like a modern Silicon Valley startup pivot. It's like a horse and buggy driver losing his carriage in a crash, and instead of giving up, he goes to engineering school at age 50 to learn how to build combustion engines.
That's a perfect analogy, actually. And that transition from sail to steam is critical to understand. It isn't just about ships going a bit faster. It fundamentally alters the economics of global trade.
Because of the reliability, right?
Yes, exactly. When you rely on wind, your supply chain is entirely stochastic. A voyage from London to New York could take 3 weeks, or it could take 3 months, depending entirely on atmospheric pressure systems that you just can't control.
And you simply cannot build a reliable, just-in-time manufacturing economy on that level of unpredictability.
You can't. Steam engines introduced something the world had never really seen on the oceans, which is schedule integrity. Steam power shifts maritime trade from a reactive endeavor to a deterministic one.
But operating a steamship requires an entirely different paradigm of knowledge, doesn't it?
Completely. You are no longer just navigating weather. Now you are managing complex internal combustion, pressure valves, coal logistics. Peter masters this, and by 1886, he secures enough capital to purchase his first steamship, the Laura.
And starts the steamship company Laura in his hometown of Svendborg, Denmark. And what I find so interesting is that he deliberately passes this new technological paradigm down to his sons.
He's not just trying to survive, he's building a modernized workforce.
Right. At a time when much of the Danish merchant fleet was still clinging to sail, he trains one son as a navigator, 2 as mechanical engineers, and his 4th son, A.P. Muller, is specifically trained in the commercial business of shipping.
And this specific division of labor really sets the foundation for the modern corporate structure. In 1904, Peter and A.P. Muller officially co-found the steamship company Svendborg, which is the direct predecessor to the massive Maersk conglomerate operating today.
But the corporate history details this fascinating internal friction that arises almost immediately regarding how to scale the business.
Yeah, they had fundamentally different visions. To understand that boardroom friction, we need to look at the mechanics of tramp shipping.
Right, which is what they were doing at the time.
Exactly. In the maritime industry, tramp shipping operates on the spot market. It is essentially the taxicab model of ocean freight. A tramp vessel has no fixed schedule and no set itinerary of port calls.
Just it goes wherever a cargo broker needs something moved, on demand.
It's highly opportunistic. If there is a sudden demand for coal in Buenos Aires, the ship goes there, unloads, and then waits for another contract to take grain back to Europe.
And while that sounds flexible, it's actually an incredibly inefficient way to scale an empire. I mean, you are constantly hunting for the next fare, you have immense periods of idle time, and you just can't establish long-term predictable revenue streams.
Exactly. Contrast that with liner shipping, which is more like a public bus route. A liner service runs a fixed route on a fixed schedule, regardless of whether the ship is full or half empty.
It allows businesses to actually plan their supply chains around your guaranteed arrival dates. But doing that requires massive scale.
It does. Transitioning to a liner model or even just dominating the tramp market requires economies of scale. You need a massive fleet to ensure you always have tonnage positioned where the market demands it.
And Maersk only had 3 ships at this point.
Right. A fleet of 3 ships leaves you highly vulnerable to localized economic downturns. So the board, acting conservatively, saw the immediate financial risk of buying more ships. But A.P. Muller saw the strategic risk of staying small.
So it's the visionary clashing with the risk managers. And A.P. Muller's response is just decisive. In 1912, he founds his own distinct entity, the Steamship Company of 1912.
Solely to secure operational independence from that conservative board.
Right. He basically bypasses the internal bureaucracy to build the capacity he knows the market will eventually demand.
And that operational independence proved to be historically vital. The world was on the brink of an era that would test the resilience of maritime trade in unprecedented ways.
The localized financial risks the board was worried about were about to be overshadowed by massive global geopolitical violence.
Exactly. We see this starkly as the sources move into the era of the First World War. The outbreak of global conflict in 1914 sends shockwaves through the maritime markets.
Freight rates completely skyrocket.
They do. Suddenly, shipping becomes an incredibly lucrative industry. But it's a prosperity built on immense physical danger. The basic laws of supply and demand became violently distorted.
Because you have naval blockades, unrestricted submarine warfare, and governments requisitioning civilian merchant fleets for military logistics, right?
Yeah, the supply of available merchant ships plummets while the demand to move wartime materials surges. Companies that managed to keep their ships afloat were charging exorbitant war risk premiums.
And there is a really revealing piece of correspondence in the archives from this period. In 1917, A.P. Meller writes a letter to his father, Peter, and he is deeply uncomfortable with the financial situation.
It's a fascinating letter.
He explicitly refers to the money they're bringing in as unnatural profits and speculation. It's just a rare moment of corporate self-awareness. He recognizes that extracting massive wealth from a catastrophic global conflict is inherently destabilizing.
And his response to that discomfort is strategically brilliant. Rather than paying out massive dividends to shareholders, he isolates that wartime capital and reinvests it into hard industrial infrastructure.
Vertical integration.
Exactly. In 1918, he uses those unnatural profits to establish the Odin Steel Shipyard. He realizes that if global events can suddenly wipe out merchant fleets, the ultimate power lies not just in operating ships, but in the capacity to manufacture them from scratch.
And that shipyard becomes a cornerstone of their empire. I mean, it operated for nearly a century until 2012, eventually pioneering some of the largest container ships in human history.
It was a massive asset.
But if the First World War was a period of uneasy profitability, the outbreak of the Second World War presented a literal existential threat to the very survival of the company and, well, to the nation of Denmark itself.
The sources outline a truly harrowing scenario here. In April 1940, German forces occupied Denmark. By this point, the Maersk fleet has expanded substantially to 46 vessels.
But crucially, 36 of those ships are operating in foreign waters outside of Danish jurisdiction.
Right. And the strategic calculus inside Maersk headquarters the night before the occupation must have been absolutely frantic. If the occupying German authorities seize administrative control of the Maersk corporate offices, they theoretically gain legal control over that entire global fleet.
And delivering 36 merchant vessels to the Axis powers would have been a massive logistical victory for the occupation.
So A.P. Muller and his son, Maersk McKinney Muller, execute what is essentially an act of corporate sabotage against the occupying force.
This part is wild. They send an emergency telegram to the captains of those 36 vessels in foreign waters, and the directive is absolute. Proceed immediately to neutral ports and deliberately ignore any future communications or orders coming from the Copenhagen headquarters.
They intentionally sever their own command and control network. They maroon their own assets to ensure they don't fall into enemy hands.
Wow.
Yeah. And those 36 ships are eventually requisitioned by the Allied forces to support the war effort, operating in incredibly hostile waters.
But the toll of that decision was staggering, wasn't it?
It really was. By the end of the Second World War, 25 Maersk vessels had been destroyed. But more importantly, 150 of their seafarers lost their lives to torpedoes, mines, and aerial bombardment.
And to manage the fragmented remnants of the fleet, operational control had to be temporarily delegated to a cousin residing in New York.
Right. Maersk McKinney Muller eventually had to navigate a dangerous journey to the U.S. just to maintain international relations and prepare for a post-war reality.
So if we step back and look at the macro-level impact of these two world wars, they exposed a glaring flaw in how the world managed its oceans. You have multinational fleets, immense loss of life, and massive economic destruction, and there is just no overarching authority to manage any of it.
Not at all.
The oceans had always been treated as the ultimate tragedy of the commons, this vast, ungovernable space where national laws just ended at the shoreline. But wait, let me ask you this. Why did it take a world war and the formation of the UN to get shipping nations to agree on basic safety rules? Weren't they already losing ships left and right before that?
It's a great question. You have to remember the tension between national sovereignty and international waters. The devastation of the 1940s finally proved that a globally integrated economy could not survive a legal vacuum on the high seas.
Because it was a jurisdictional nightmare.
An
Right?
absolute nightmare. You had ships being built in British yards, owned by Danish corporations, crewed by multinational sailors, transporting goods between the Americas and Asia. When a collision occurs or a ship sinks due to poor structural standards, resolving the liability was just impossible.
Everybody pointing fingers at everybody else.
Exactly. Nations were fiercely protective of their maritime sovereignty. They absolutely did not want an international body dictating the engineering standards of their domestic fleets.
But the collective trauma of the war forces a shift. In 1948, under the newly formed United Nations architecture, a conference is convened in Geneva.
And the result is a treaty establishing the Intergovernmental Maritime Consultative Organization, or IMCO, which we know today as the IMO, the International Maritime Organization.
Which formally enters into force in 1958. This is a monumental pivot in international law. Governments willingly sat at a table and conceded that standardizing safety and efficiency on the oceans was actually more important than absolute isolated national sovereignty.
Yes. And their mandate is spelled out in Article 1A of the IMO Convention. The goal is to provide the machinery for cooperation among governments and to encourage the highest practicable standards in maritime safety, efficiency, and pollution control.
They literally had to engineer a bureaucratic machine to manage the physical machines.
Precisely. And their immediate priority was updating the SOLAS Treaty, the Safety of Life at Sea Convention, so they established the global referee. But almost immediately, the actual mechanics of how cargo moved were about to undergo a revolution that would test every single limitation of this newly formed regulatory body.
Right. We were entering the era of the shipping container.
Yes, and to really grasp the magnitude of the shipping container, we have to look at the economic and logistical nightmare of the system it replaced.
Break bulk cargo.
Exactly. For centuries, the global supply chain relied on break bulk cargo. This is a highly labor-intensive process. You are dealing with cargo in its raw individual packaging. We are talking about hundreds of sacks of coffee beans, massive wooden crates holding industrial machinery, loose bundles of timber, individual barrels of liquid.
It is essentially a chaotic, dangerous, three-dimensional jigsaw puzzle. Like when a break bulk ship arrives at a port, it triggers this massive mobilization of manual labor. Stevedores and longshoremen have to physically descend into the hull of the ship, manually rig cargo nets around these disparate items, and hoist them out piece by piece.
And I mean, the economic friction of that whole process is just massive. A merchant vessel might spend an equal amount of time sitting idle at a dock, being loaded and unloaded as it did actually traversing the ocean.
Which is incredibly expensive.
Hugely expensive. In the logistics industry, idle time at a port incurs massive costs known as demurrage. Furthermore, every time human hands touch the cargo, the probability of damage skyrockets.
Not to mention the theft, right? Break bulk shipping was notorious for pilferage. There's this historical concept of dockers' wages, where it was essentially an accepted operational loss that a certain percentage of the whiskey, coffee, or high-value goods being unloaded would just disappear into the pockets of the laborers.
It was just baked into the cost of doing business.
Yeah, the bottleneck of global trade wasn't the top speed of the ship. It was the physical limitation of human hands at the dock.
And the solution to this bottleneck comes in 1956. And interestingly, it doesn't originate from a naval architect or a maritime insider. It comes from Malcolm McLean, a man who owned a terrestrial trucking company in the United States.
The origin story here is brilliant in its simplicity. McLean is sitting at a busy port, watching the clock tick for hours as stevedores manually empty the contents of his truck trailer, item by item, just to lower those individual items into the hull of his ship. He realizes he is paying for massive inefficiencies.
He identifies a fundamental flaw in the logic of transit. He looks at his truck trailer and asks a paradigm-shifting question. Why are we unpacking the box?
Right?
Why don't we simply detach the entire steel trailer from the truck chassis, hoist the entire box onto the ship, and leave the cargo untouched inside?
It is the conceptual shift from moving the contents to moving the packaging. In April of 1956, McLean tests this theory. He takes a converted oil tanker named the Ideal X, loads it with 58 of these early standardized steel containers, and sails it from Newark, New Jersey to Houston, Texas.
Now, moving 58 containers seems quaint by modern standards, but the economic data from that voyage altered the course of human history. The cost of loading break bulk cargo at the time was roughly $5.86 per ton.
Okay.
McLean loaded the Ideal X for less than 16 cents per ton. He reduced the cost of loading a ship by over 97%.
97%. That economic deflation completely upends the maritime world. But our Maersk sources indicate that the established shipping titans didn't immediately pivot. I mean, in 1958, Maersk McKinney Miller is quoted expressing a desire for clients to come to them for anything transportation-wise.
Yeah, they viewed themselves as bespoke problem solvers, not just box movers.
Why the hesitation, though, with those kinds of cost savings?
Well, their hesitation is actually economically rational if you look at the systemic requirements of containerization. You cannot simply buy a few steel boxes and put them on a traditional break-bulk ship. The container demands an entirely new, deeply integrated physical ecosystem.
Ah,
You need ships specifically designed with cellular guides to hold the boxes rigidly in place. You need ports willing to invest millions in massive gantry cranes capable of lifting 30-ton loads. You need rail and trucking networks standardized to accept the exact dimensions of the box.
so it's similar to the tech industry trying to agree on a universal standard, like the USB-C charging cable. If one manufacturer uses a proprietary cable and another uses something slightly different, the whole ecosystem fragments.
Exactly.
The container only works if the crane operator in Rotterdam, the truck driver in Chicago, and the shipbuilder in South Korea are all operating on the exact same geometric parameters.
Precisely. The initial capital expenditure required to transition to this system was astronomical, but the efficiency gains eventually made it unavoidable. Maersk fully commits to the transition in the 1970s.
Yeah, in September 1975, they launched their first fully containerized service when the Adrian Maersk departs Port Elizabeth on the U.S. East Coast, carrying 385 containers.
And from that point on, the growth curve just goes vertical. Throughout the late 70s and 80s, container shipping experiences consistent 20% annual growth.
The sources referred to the shipping container and the digital barcode as the hidden enablers of world trade.
It's so true. By standardizing the physical unit of transport, they effectively commoditized distance. When shipping costs drop to a fraction of a percent of a product's retail value, it fundamentally alters global manufacturing.
It suddenly becomes economically viable to source raw materials in South America, manufacture subcomponents in Southeast Asia, assemble the final product in Mexico, and sell it in European markets.
The container literally birthed the highly distributed, modern, global supply chain.
Which brings us to a massive, kind of overlooked engineering crisis. The container is to global trade what the standardized shipping pallet is to a warehouse. It removes the thinking from the packing. But wait, if everyone is suddenly using millions of these heavy steel boxes, how do we know they won't just collapse on each other?
That is the precise crisis that forced the IMO to intervene. Containerization solved an economic problem, but it generated a terrifying structural physics problem.
Because if a single container at the base of a stack suffers structural failure and crumples,
The entire stack loses its center of gravity and collapses. You could potentially take hundreds of surrounding containers over the side of the vessel. You can't just trust that a box built in a random factory can survive the dynamic loads of the open ocean.
and that forces the creation of one of the most technical and critical sources in our stack today, the 1972 Convention for Safe Containers, or the CSC 1972. The IMO and the UN basically recognized that this physical object needed a globally recognized passport.
Right. And the CSC in 1972 was drafted to navigate a very delicate geopolitical and engineering balance. The treaty establishes two primary goals. Goal 1 is straightforward engineering, protecting human life in the transport and handling of containers by establishing rigorous, globally acceptable testing procedures and strength requirements.
We need mathematical proof that the corner fittings won't shear off when a crane lifts 30 tons, and that the vertical pillars can withstand massive compressive forces.
Exactly. But Goal 2 is where we see the geopolitical nuance. The treaty aims to facilitate international transport by actively preventing a confusing proliferation of different national safety regulations.
Yeah, because if we allow individual nations to dictate container engineering, the economic miracle of the container dies instantly, right?
Immediately.
Like if the U.S. mandates that containers must be constructed with half-inch high-tensile steel, but France demands specific torsion testing, and Japan requires a completely different welding standard, I mean, the entire frictionless network shatters.
A ship arriving in a foreign port would have to sit idle for weeks while local inspectors verified that every single box met their specific domestic codes. That kind of regulatory patchwork would introduce more friction than the old break-bulk system.
So what did the treaty actually do?
The CSC in 1972 essentially targets any international freight container of a prescribed minimum size, specifically focusing on those equipped with standardized corner fittings. Those corner fittings are the structural anchors of the entire system. They are how the box is locked to the cranes, the truck chassis, and to each other on the ship.
And the treaty implements this brilliant mechanism to manage this global standardization. the safety approval plate. It's a physical, standardized metal plate that must be permanently welded or riveted to every single container operating internationally.
Yes, the plate is the tangible manifestation of the treaty's power. It contains the vital, standardized technical data, the maximum operating gross mass, the allowable stacking capacity in kilograms, the dates of its structural examinations, and the identification of the testing authority.
Okay, let's unpack this for a second. The IMO basically created a global visa system for inanimate objects.
That's exactly what it is.
Without that plate, the box is stateless and illegal. If a container arrives at a port bearing a valid safety approval plate, it is a trusted citizen of the global supply chain.
And the diplomatic engine that makes this visa system function is a concept the treaty calls reciprocal acceptance.
Which means what, exactly?
It means that if the government of the United Kingdom or an engineering firm authorized by them conducts the structural tests and issues a safety approval plate to a container, the governments of the United States, China, Brazil, and every other signatory nation are legally bound to recognize that approval.
They are forced to trust a foreign bureaucracy's engineering assessment.
Exactly. This allows containers to cross borders and be loaded onto foreign vessels with what the treaty describes as minimum safety control formalities. It is a stunning surrender of border inspection sovereignty.
Because the economic incentive of frictionless trade vastly outweighed their desire for localized control.
Right. But steel degrades. A container operating in a highly corrosive saltwater environment, being violently dropped onto concrete docks by massive cranes, is going to suffer structural fatigue. You can't just test it once in 1975 and assume it's safe forever.
So the CSC 1972 mandates strict, ongoing maintenance protocols.
Yes, the convention clearly places the burden of maintenance squarely on the owner of the container. Initially, the treaty demanded that an approved container undergo a physical re-examination every 30 months to ensure it maintained its original structural integrity.
But the reality of tracking millions of boxes across the globe forced the regulations to evolve. The sources detail a continuous stream of amendments to the CSC 1972. Like in 1983, they recognized that a strict 30-month calendar was logistically impossible for massive fleets, so they introduced an amendment allowing for continuous examination programs based on the actual usage and routing of the boxes.
And the amendments also respond to specific operational abuses. In 1991, the IMO adopted rules strictly prohibiting containers from displaying misleading maximum gross weight information.
Which makes perfect sense when you consider the physics of shiploading. A modern ship's stability is calculated entirely by a computer model that relies on the declared weight of each container.
Right.
If you have hundreds of shippers lying about how heavy their boxes are to save money on freight rates, you end up placing heavily overloaded boxes high up in the stack. That raises the center of gravity of the entire vessel and can cause the ship to literally break its own back or capsize in heavy seas.
The regulations must constantly chase the physical realities of the trade. Look at the 2012 amendments under Resolution MSC 23088. This is a fascinating piece of engineering regulation. It introduces strict new testing parameters for containers that are approved to operate with one door removed.
Now, to a layperson, operating a shipping container without a door sounds absurd. Why would you compromise a sealed box?
It happens in highly specialized logistical scenarios. Sometimes shippers need to transport agricultural products that require massive ambient ventilation, or they're transporting specialized industrial components that are just a few inches too long for standard dimensions.
But removing the door fundamentally alters the structural physics of the object.
Completely.
A container is a rigid, six-sided box. The structural integrity, particularly its resistance to shear stress and torsion, relies on all six sides being intact. If you remove a door, you turn a rigid box into a U-shape.
Yep.
So when that container is stacked at the bottom of a hold and the ship begins to violently roll in a storm, the lateral forces will cause that U-shape to just twist and shear apart.
Exactly. The 2012 amendment recognized this specific danger and mandated that if a container is to be certified for operation without a door, it must undergo specific, rigorous mathematical and physical torsion testing to prove it can withstand those shear forces.
And they also empowered authorized port officers with specific control measures, allowing them to legally halt the transit of any container if they observe visible damage to structurally sensitive components, regardless of whether it has a valid approval plate.
The rulebook is constantly expanding. In 2014, Resolution MSC.35592 standardized all the physical testing measurements to the metric SI system and formalized the markings for containers that have restricted stacking capacities. It is a living, breathing treaty designed to manage the physics of global trade.
But all of these rigorous regulations governing the containers are kind of moot if we don't understand the engineering required to build the vessels that carry them.
Very true.
To grasp the modern scale of this industry, we need to transition from the rules of the steel boxes to the physical construction of the megaships. And our Maersk source material gives us incredible ground-level insight into this through the perspective of a man named Mikkel Jacobsen.
Right, the machinery superintendent for the Maersk site team.
Yeah, his life illustrates the extreme geographic dispersion of modern shipbuilding. He relocated his entire family, including 3-year-old twins, from Denmark to Ulsan, South Korea.
He was deployed to oversee construction at Hyundai Heavy Industries, or HHI. This is one of the largest, most technologically advanced shipbuilding facilities on the planet.
The scale of what HHI does is just difficult to comprehend.
They're not merely building ships, they are operating massive industrial cities dedicated to maritime assembly.
And Mikkel breaks down the construction timeline of a modern megaship, and it highlights just how far we've come from the days of laying down a wooden keel. The process begins in massive production halls with the steel cutting phase.
It is a highly automated process. A single command on a computer terminal ignites gas flames that slice through massive, high-tensile steel plates with absolute laser precision. This is the industrial genesis of a new vessel.
Once those plates are cut, they move into what Mikkel accurately describes as the Lego phase. The shipyard's whole team takes these thousands of individual steel pieces and begins welding them into enormous, multi-story structural blocks.
These blocks are essentially self-contained cross-sections of the ship. Once assembled, they undergo extensive surface treatment, and this is far more complex than just making the ship look presentable.
Right, because while the exterior hull receives layers of the iconic Maersk blue paint to reduce hydrodynamic drag and resist saltwater corrosion, the interior spaces undergo highly specialized coatings.
They have to. The interior of these ships contains massive ballast tanks and cargo holds that will be exposed to incredible internal stresses and corrosive materials. You have to chemically seal the steel before the ship is even assembled.
After the blocks are treated, the shipyard reaches a major milestone known as keel laying. This is when the first of these massive prefabricated blocks is carefully lowered by gantry cranes into a massive dry dock.
The dry dock is essentially a massive concrete basin built below sea level, kept dry by heavy water pumps. And once that first block is down, the outfitting phase begins, and it is just a logistical sprint. They are welding thousands of tons of steel into place every single day.
The orchestration is phenomenal. While the whole blocks are being welded together, massive internal components are being dropped into the open structure.
Like the main engine.
Yeah, which is often the size of a multi-story building itself and produces tens of thousands of horsepower. That's lowered into the engine room block. Simultaneously, teams are routing thousands of miles of electrical cabling, installing navigational systems, and fitting the crew accommodations.
It's the equivalent of building a 1,300-foot-long skyscraper horizontally, dropping a massive power plant into its basement, wiring the entire grid, and doing it all in a matter of months.
That is just insane. And once the external hull is fully sealed and welded, they initiate the launching phase. And the physics of a dry dock launch are fascinating.
Yeah.
You don't just push it into the water, you bring the ocean to the ship.
It is a highly controlled physical operation. Giant valves in the concrete basin are open, and thousands of liters of seawater pour into the dry dock every second. The objective is to slowly, calculatedly introduce buoyancy.
Over several tense hours, the rising water displaces the massive weight of the steel hull.
And the ship slowly lifts off the massive wooden or concrete blocks it was built upon. It becomes buoyant for the first time. By the next morning, a fleet of tugboats carefully maneuvers the floating Leviathan out of the flooded dock and over to the outfitting quay for final mechanical testing.
The construction of a vessel of this magnitude is a masterclass in supply chain management itself. Every single component, from the raw steel plate to the complex radar arrays down to the specialized paint, must arrive at the shipyard in South Korea exactly when the production schedule dictates.
Because if a crucial engine component is delayed in transit, an entire multi-million-dollar dry dock sits idle. It completely cascades the financial timeline of the build.
And the ships that Mikkel Jacobsen is currently building in South Korea represent a massive inflection point in our story. Because for the first century of mechanized shipping, the primary engineering goals were simply to build ships bigger, faster, and structurally robust enough to survive the physics of the ocean.
Right.
But today, the shipping industry is facing an entirely new category of existential threat.
The mandate of both the IMO and the major shipping conglomerates has expanded far beyond basic structural safety and trade facilitation. They are now actively attempting to manage the immense environmental and geopolitical footprint of a fleet that burns millions of tons of fuel a day.
We can actually trace this expanding regulatory mandate directly through the IMO's history. The initial shift toward environmental protection was violently catalyzed by the Torrey Canyon disaster in 1967.
The Torrey Canyon was a supertanker that struck a reef off the coast of the United Kingdom, rupturing its hull and spilling roughly 120,000 tons of crude oil into the ocean.
Wow.
Yeah, it was an ecological catastrophe of a scale the world had never witnessed. It proved that as ships scaled up in size, the potential for catastrophic environmental destruction scaled exponentially alongside them.
This disaster forced the IMO to act quickly, drafting the MARPOL Convention, which is a foundational international treaty for the prevention of pollution from ships. But regulating pollution quickly evolved beyond just preventing massive oil spills.
It did. The sources show a cascading series of environmental regulations as our understanding of marine ecology deepened. In 2001, the IMO adopted rules regulating anti-fouling systems.
Because for decades, ships used highly toxic paints on their hulls to prevent barnacles and algae from attaching and creating drag. But those toxic chemicals were slowly leaching into the oceans and devastating local marine life.
Exactly. And then in 2004, they addressed a bizarre biological threat: ballast water management.
Oh.
Ships pump millions of gallons of seawater into internal tanks to maintain stability when they aren't carrying cargo. But when a ship sucks up seawater in a port in Asia and discharges it in a port in North America, it transports billions of microscopic organisms and invasive species.
Which can completely collapse foreign ecosystems. So the IMO had to mandate systems to sterilize that water. And in 2009, they adopted protocols for ship recycling, trying to regulate the incredibly dangerous industry of breaking down massive steel ships containing asbestos and heavy metals on beaches in developing nations.
Parallel to this environmental awakening was a profound shift in maritime security. The September 11th terrorist attacks fundamentally altered global risk assessments. The world realized that the hyper-efficient, highly standardized container network was incredibly vulnerable to exploitation by bad actors.
If a container can move frictionlessly across borders, so can a weapon.
Exactly. In 2004, the IMO introduced the ISPS Code, establishing a comprehensive mandatory security regime for international shipping and port facilities. And in 2005, they adopted the SUA protocols, the suppression of unlawful acts,
which represent a massive concession of traditional maritime sovereignty. They established a legal framework allowing the naval or Coast Guard forces of one nation to intercept and board a merchant ship flying the flag of a different nation in international waters, provided they have reasonable grounds to suspect the vessel is involved in terrorism or the transport of weapons of mass destruction.
The days of a ship being a completely untouchable floating island of sovereign territory are over. The tragedy of the commons on the oceans is slowly being closed by these aggressive collective agreements.
But the ultimate test of this international cooperation is the current climate crisis. The shipping industry is responsible for roughly 3% of global greenhouse gas emissions. That is roughly equivalent to the total carbon output of a major industrialized nation like Germany or Japan.
It's massive. And the IMO explicitly aligned its mission with the United Nations Sustainable Development Goal 13, taking urgent action to combat climate change.
Our sources note that they adopted an initial greenhouse gas strategy in 2018, but the scientific reality forced a much more aggressive pivot.
Yeah, in 2023, they adopted a revised strategy. The mandate is now to urgently phase out greenhouse gas emissions from international shipping entirely, targeting net zero emissions by or around 2050, while ensuring a just and equitable transition.
That phrase, just and equitable transition, acknowledges the severe economic friction this will cause. Forcing the global fleet to abandon cheap, energy-dense fossil fuels will disproportionately impact developing nations that rely on low-cost shipping for their economic survival.
Which brings us directly back to Maersk and what Mikkel Jacobsen is overseeing in that South Korean shipyard. Maersk didn't passively wait for the IMO regulations to force their hand.
The corporate history shows that in 2016, they executed a radical strategic pivot.
For decades, A.P. Møller-Maersk operated as a sprawling conglomerate. They were deeply involved in offshore drilling, oil tankers, and fossil fuel extraction alongside their container business. In 2016, they made the difficult strategic decision to divest from the oil and energy sectors entirely.
They restructured the entire corporation to focus exclusively on being a global integrator of container logistics. They committed to the supply chain and walked away from the oil.
And the massive new build vessels Mikkel is currently constructing in Ulsan are the physical manifestation of that pivot. These ships are revolutionary because they are engineered to sail on green methanol.
Now wait, so what does this all mean? We spent 100 years trying to make ships bigger and faster using heavy fuel oil, and now we have to reverse engineer them to be completely green while still carrying 18,000 containers.
That's the challenge. To appreciate the engineering challenge here, you have to understand maritime propulsion. For a century, cargo ships have burned heavy fuel oil, or bunker fuel. It is thick, highly toxic, incredibly energy-dense, and very cheap. Replacing it requires a complete reimagining of the ship's architecture.
Because green methanol isn't just regular fuel with a better marketing name. It is chemically synthesized using renewable energy and captured carbon dioxide.
The critical difference is the carbon cycle. When the ship burns green methanol, the carbon it releases is equal to the carbon that was initially captured to create it. It does not add new carbon to the atmosphere.
However, the engineering trade-off is severe.
Very severe. Clean methanol has roughly half the volumetric energy density of traditional bunker fuel. This means a ship must carry twice as much fuel to travel the same distance.
So when Mikkel's team builds these new ships, they have to completely redesign the internal architecture, dedicating massive amounts of potential cargo space to much larger, highly specialized fuel tanks.
It really contextualizes the magnitude of the challenge. We spent over a century refining the internal combustion engine, figuring out how to build gargantuan ships that can efficiently move 18,000 containers across the Pacific using the cheapest fuel possible.
And now, at the absolute peak of our engineering mastery of that fossil fuel system, we have to completely rip out the propulsion architecture and reverse engineer it to run on complex, low-density green fuels, all without breaking the economic efficiency that makes global trade possible.
If you synthesize the historical arc we have mapped out today, the evolution is astounding. We began with Peter Maersk battling the stochastic, unpredictable violence of the wind and weather in 1883, just trying to keep a wooden hull from shattering on a Scottish reef.
And then we moved to A.P. Møller frantically attempting to hide a massive corporate fleet from the predatory threat of U-boats and naval blockades in the 1940s.
We saw how the catastrophic losses of those wars forced nations to surrender their absolute maritime sovereignty, creating the IMO in 1958 to establish a global rulebook.
We explored how Malcolm McLean's 1956 realization that you should move the packaging, not the cargo, triggered an explosion of standardized steel boxes that shrunk the world economy.
We examined how the CSC 1972 treaty had to mathematically guarantee the physical safety of those boxes while preventing bureaucratic bottlenecks.
And finally, we arrive at the modern shipyard, where the enemy is no longer just the weather or a foreign navy, but invisible greenhouse gases altering the planetary climate.
The entire focus of global maritime regulation has shifted from merely ensuring the survival of the vessel to ensuring the survival of the biosphere itself.
It is a continuous narrative of human engineering and diplomatic ingenuity scaling up to meet the terrifying vastness of the ocean. But before we wrap up, I want to leave you with a different angle to think about the next time you see a shipping container rolling down the highway or stacked at a port. We have spent this entire deep dive analyzing the macro-level systems. The physical hardware, the steel boxes, the massive dry docks, the global treaties, and the chemistry of green methanol engines. But as these massive leviathans become greener, increasingly gigantic and heavily digitized, what is happening to the human beings operating them?
That's a great point.
The seafarer of 1904 wrestled directly with the physical elements, the wind, the rigging, and the grueling labor of the coal furnace. The seafarer of today is increasingly managing a floating, highly automated green methanol supercomputer. They are monitoring digital readouts in a climate-controlled bridge hundreds of feet above the water.
It's a completely different job.
It is. As the shipping industry becomes perfectly optimized, mathematically modeled, and technologically advanced, do the inherent romance and visceral reality of the sea disappear entirely? Or has the experience of the mariners simply evolved into an entirely different kind of technological frontier?
That is the philosophical question that the next generation of maritime engineers and seafarers will have to navigate as they take control of this evolving global network.
And on that note, I want to thank you for joining us on this deep dive into the hidden architecture of the oceans. I highly doubt you will ever look at a simple corrugated steel box exactly the same way again.
that brings another quiet episode of Sleepcast to an end. Thank you for spending this time with us. We hope our two hosts helped you relax, slow your thoughts, and perhaps drift gently off to sleep. New episodes of Sleepcast are released every day, 7 days a week, all year round. Follow Sleepcast on the podcast app you are using now, so new episodes are added automatically, and you can be notified whenever another wonderfully boring story is released. Until next time, sleep peacefully and good night. Sleepcast, probably the most boring podcast in the world.